Okay, so now we're going to go over the Buckingham Pi Theorem, and I'm going to discuss how to use it mainly by example. So for the Buckingham Pi Theorem, we're going to the first part. We're going to let f be a function of n of physical variables p, where the p here represents a physical variable and n represents the number of physical variables. Okay, and we're going to just define this f to be f of the first physical variable, the second physical variable, all the way to the nth physical variable to be equal to 0. So we need to define our function if we're going to use this Buckingham Pi theorem to achieve similarity or learn how to achieve similarity. We need to arrange our quantity of interest to be inside of a function that is set equal to 0. So in our drag example, we say the drag force D, and the book calls that F, but I'm just used to using D for that. D will be equal to some drag force function, and that's a function of all of our physical variables that we selected. So that'd be V infinity, rho infinity, the viscosity far away from the object, speed of sound, and the diameter of the object. And we need to rearrange this function here into a single function that is equal to 0. So need to rearrange to a function equal to 0. So we could say that our drag force function Fd minus d itself is equal to 0, because all I've done was I moved d over to this side and I subtracted both sides by d. And then this will be equal, this will be equal to some f1. Okay? And then this f1 is some function of d, v infinity, rho infinity, mu infinity, speed of sound, and d. Okay. And so we have arranged this function to be into just a single function that's equal to 0. And now we need to find the number. We need to find n, and n is the number of physical variables. And so really all we do is just count the number of arguments to this function. So counting gives n equals 6 physical variables. Okay. Now step B is on these physical variables, we need to examine the units. Okay, and you have two choices for this. You could work in and you have two choices. You could work in the mass, length, time, temperature, etc., or force, length, time, temperature, etc. Okay, it is up to you. Which one you choose. I typically like to use the mass-based system, and so I'm going to do all my examples in the mass-based system. In some other cases, it's more straightforward to use the force system. Note, after we go through this entire procedure, the final result should not depend on which of these two systems you pick. Okay? And so I'm going to choose mass. And so I'm going to choose, and that's just a choice, the mass, length, and time. Okay, and T for temp if you're working with temperature. Okay? And then you examine the units of all of the physical variables. And so examine the units of all physical variables. Okay, and so we have the drag force, and so we have the physical variable, and the units. Okay, well, we have the drag force. That has units of force, which is equal to mass times acceleration, which is mass times length over time squared. Okay. We have V infinity, and those units are meters per second, are really length over time. We have rho infinity, which is just a density, and so that is a mass per unit volume, or mass divided by L cubed. We have viscosity, and recall that that has units of Pascal seconds, and you can work through the units, and that turns out to be force times time if you're working in the force system, which is equal to mass over length times time. Okay, and so that's the units of that. There's the speed of sound, A infinity, and that's just a velocity, so the units of that are length per unit time. And then there's the diameter of the sphere D, and that just is simply a length. Okay, and so we count the number of different types of units here, and I'll be working in the mass-based system, so I'll only be looking at the ones that involve mass, not the ones that involve force. And so we count the number of different units, and we have mass, we have length, and we have time. Okay, and so with mass, length, and time, mass, length, time, length that's not a new unit, time that's not a new unit, mass that's not a new unit, length that's length cubed, and so that just involves length, that's not a new unit. Mass, that's not a new unit, length, time, and so here, if you count the total number of units, there are three units, or three base units, and so that would be mass, length, and time. Okay, and so basically the drag force, the velocity, the density, the viscosity, the speed of sound, and the diameter can be expressed in terms of mass, length, and time. And now, if you use the force-based system, you would still have three units. It's just they would be, if used force, you would have F, L, and T as your units, because you would have to express the density in terms of force rather than mass. Okay, so you cannot mix and match the force-based system over here with the mass-based system. Okay, and so we will call, I'll call the number of units K. And so for this, K equals 3. Okay, and now usually equals K. And so for this example, K is equal to 3. And now, according to the Buckingham Pi Theorem, arrange our function f1 of d, v infinity, rho infinity, mu infinity, a infinity, and d into a function of n minus k variables. And now there is a small caveat to this that almost never occurs, is that this is usually the case, but not always. And I'll discuss this a bit later on, and you can see example 7.3 as a situation when that occurs. Okay, and so, but in this case, we for the example here, we do not need to worry about this special case. That in practice you'll probably only run into, and if you do run into it, it'll only be a few times in your career. Okay, so then according to Buckingham Pi, we can arrange this into n minus k, which is 6 minus 3, of variables. So we'll have f, and I'll call this 2, is a function of a new variable pi 1, a new variable pi 2, and a new variable pi n minus k. Okay, and so our new function, we have taken a function of 6 variables here and have turned it into a function of 3 variables down here. And so now it remains to be determined what this function f2, what pi 1, pi 2, and pi 3 are. So these pi terms are the new variables. Okay. And these are and these will be determined as functions of the physical variables cat p. Okay? And so how we go about finding pi 1, pi 2, and pi 3, again, this Buckingham Pi Theorem, it's going to seem crazy and abstract and weird at first, but it is literally one of those things, if you do it once or twice, you'll start to get the hang of it. And it's actually, it's one of those things, it is much harder to explain than it is to actually do. Okay, and so how we find these new pi variables. Okay, well, we'll say that pi 1 equals some f of pi 1, and this will be a function of a physical variable 1, physical variable 2, physical variable up to physical variable k, and an additional variable, an additional physical variable k plus 1. Okay, and so recall for this, k is the number of dimensions, and so k is the number of dimensions, and we have a second pi variable that will be a function of pi 1, the first physical variable, the second physical variable, and the kth physical variable. Plus, in addition, it's a function of another physical variable, and I'll call that k plus 2. Okay, and then you go all the way down to pi n minus k, or the last pi variable, and that's equal to some function of pi n minus k, and that's again a function of, I'm going to move this over a little bit, a function of the first physical variable, the second physical variable, and the kth physical variable, and Pn. Okay? And so, and so you notice in this Buckingham Pi, all of these pi variables are going to be functions of the same k physical variables, and each and a different variable for each. Let me close this. And so this grouping of variables here, might as well use just a different color. These are called the repeating variables. Okay, and these here are the non-repeating variables. Okay. And so these pi n minus k variables, or functions, have the same k repeating of variables. And that is with exceptions of those very few special cases. And now the question is that if we go that our drag force is a function of 6 different things, and k is equal to 3. So how do we pick P1, P2, and Pk? Well, to some extent it is a little bit arbitrary, but there are some rules to pick these repeating variables, and some of these are very hard, rigorous rules based on Buckingham's theorem itself, and some are just based off of good engineering practice and experience. And so these repeating variables must have all of the base units between them. Okay, and so that is, if you had a problem that has mass, length, and time, that is your choice of the repeating variables over here. Between them, they must have the units of mass, length, and time. Okay, so you could not choose something that had, say you had an area and a volume and a length. You could not choose P1 to be a length, P2 to be an area, and P3 to be a volume, because those all involve length. Okay, and you're not picking up mass or time. Okay, so the repeating variables here must involve all of the base units. Okay, and a very hard rule that you cannot break is they cannot have the quantity you are measuring. Okay, and that is the drag force in this case. Okay, so you cannot, for our drag example, you cannot pick the drag force as one of the repeating variables. If you're doing experiments to measure the pressure drop in a piping system, you're trying to measure the pressure drop in the piping system, so you cannot pick the pressure drop to be one of the repeating variables. So the quantity of interest cannot be one of the repeating variables. And two of the repeating variables cannot have the same units. Okay, so for our drag example, we could not use both V infinity and A infinity as two repeating variables. Okay, we simply cannot, because V infinity and A infinity have the same units. Okay, and now the other ones are arbitrary. So these three here are the rules that you cannot break for Buckingham Pi to work. Okay, and the remaining repeated variables, there is a bit of arbitrariness to it, but in good engineering practice, you pick the ones that you have the most control over in the experiment. So the rest are somewhat arbitrary, but pick ones you have the most control over. Okay, and so typically that would be, say you're going to measure drag force in a wind tunnel, you have direct control of the free stream velocity, you have direct control over the size of the object, and you have direct control over rho infinity quite often, because this would be the velocity in the wind tunnel or water tunnel or whatever. You have control over the size of the model, and you can control often the gas or fluid, so you can control which fluid you use. Okay. And so in general, for the other repeating variables, you just need to think about how you're going to do the experiment and pick the things that you have the most control over. You don't have a whole lot of control over the viscosity, so you typically wouldn't pick viscosity to be one of the repeating variables. Okay? And so for our drag problem, we choose V infinity, D, and rho infinity. Oops, that's a really bad rho. Rho infinity to be the repeating variables. Okay, And so we just need to verify, A, we have not picked the drag force, so we have satisfied this first rule here. And now we need to check the second criterion, and that the repeating variables should have all the units between them, and two of them should not have the same units. So let's make sure that that's true. Well, we found that this was length over time for the units. This was length, and this was mass per length cubed. And so we have time, which is here. We have length, and we have mass. So we have all three of our units between them, and none of these have the same units. Okay? And they're not linear combinations of one another. Okay, and so these are all good. So this is a good valid set of repeating variables. Okay? And so if we choose v infinity d and rho infinity to be the repeating variables, the leftover variables are the non-repeating of variables. Okay, so then for the drag example, pi 1 equals sum f of pi 1, and that's a function of our repeating variables, which we've chosen to be rho infinity, v infinity, d, and our non-repeating variable, and the first non-repeating variable is the quantity of interest, our QOI. Pi 2 equals some function of pi 2, and that will be a function of our repeating variables, v infinity, d, and it's a function of mu infinity. And pi 3, and this will be equal to a function of pi 3, which is a function of the repeating variables rho infinity, v infinity, d, and the speed of sound. Okay. So now we need to find these pi. So now we need to find the pi variables. Okay, and I will do that in the next video. Yes.